In this video, I'm going to teach you everything that you ever wanted or didn't want to know about empirical formulas. That's the topic of conversation today, empirical formulas. An empirical formula consists of the element symbols and subscripts that show the lowest whole number ratio of atoms in a compound. The most important words in that definition would be lowest whole number ratio. So that's what you want to keep in mind as we're going through and doing these problems. We're dealing with the lowest whole number ratio of atoms in a compound. And in order to do this, you need the composition data. Now, what's interesting about empirical formula problems is this is the exact opposite of what we were doing when we did percent composition. When we did percent composition, we started here with the ratio, and we went in this direction. We figured out, okay, there are 2 moles of sulfur for every 1 mole of oxygen in the compound. And then we looked on the periodic table and we got the molar mass. And then we did a percent calculation and ended up with percent. So in percent composition, we started with the formula, which is the ratio, and we ended up with percent. In empirical formula problems, we're going to do the opposite. We're going to start with percent, and we're going to work towards the ratio or formula. Let's take a look at our first example. The first example says, find the empirical formula for a compound that contains 26.56% potassium, 35.41% chromium, and 38.03% oxygen. So again, keeping in mind that little flow chart we had, we're starting with percent, going to grams, going to moles, and then figuring out our ratio. So to start with percent and change it into grams, that's kind of easy because we're going to assume each time that we have 100 grams of the compound. So if we have 100 grams of the compound, we can say that we have 26.56 grams of potassium, 35.41 grams of chromium, and what was the last one? 38.03 grams of oxygen. So again, all we did so far was take off the percent and put grams behind each one. And what allows us to do that is we're assuming we have 100 grams of the compound. So after grams, we convert to moles. This you already know how to do. So for each one, we're going to do a gram to mole conversion. I'm going to put grams of potassium on the bottom to cancel out, moles of potassium on the top because that's what I want, grams of chromium on the bottom to cancel out, moles of chromium on the top, grams of oxygen on the bottom to cancel out, moles of oxygen on the top. And then you go to your periodic table and look up some molar masses. So the molar mass of potassium, look on the left side of your periodic table, and you'll see 39.098. Chromium, that'll be in the middle, 51.996. And maybe you have oxygen memorized by now. If not, look on the upper right-hand corner. Oxygen is 15.999. So then grab your calculator. Pause if you need to. We'll do the math here. So I take 26.56 divided by 39.098, and I get 0.6793. The only reason that I'm keeping 4 digits here is because I started with 4 significant figures in the beginning, so I kind of carry 4 significant figures through. For the next one, I get 0.6810, and this would be moles of potassium. Let's get some labels on there. And then 2.377 moles of oxygen. So again, all we did was we took each one and we did a gram to mole conversion for each one. So now we're at this stage right here where we have moles and we need to figure out the ratio. Well, the trick to getting the ratio is you look at your 3 numbers that you have for moles and then you divide each one by the smallest. So if I look at these three numbers, the smallest would be this first one, 0.6793. So I'm going to divide all three of these numbers by the smallest, 0.6793. Okay, so this one's going to come out to 1. If you divide this one, 0.6810 divided by 0.6793, you get 1.0025, which we're going to round to 1. And then the last one, I get 3.499, which I'm going to round to 3.5. Now, let me pause here and talk to you a little bit about the rounding. When you get to this point where you've divided each by the smallest, what you're going to do is look to round to whole numbers, halves, thirds, or quarters. If you've done all your math correctly, these numbers will either come out to really, really close to whole numbers, halves like this one, 3.5. It could be thirds like 3.33 or 3.67, or quarters, 3.25 or 3.75. At this point now we have a ratio 1 to 1 to 3.5. But if I wrote the formula, let's see, 1 potassium to every 1 chromium to 3.5 oxygen, that formula looks weird, KCr03.5. The reason is because it has to be a whole number. Empirical formulas have to be the lowest whole number ratio. This isn't a whole number, it's a half. So when you have a half, after you get to this point where you divide each by the smallest, what you can do is double everything. If I multiply each of these by 2, I'll write the formula down here just because of space, I get K2, and then Cr2, and then 3.5 times 2 would be 7, and that is my empirical formula. I can't reduce that any further. I can't simplify it. A 2 to 2 to 7 ratio is the lowest whole number ratio that those atoms are in this compound. So just to recap, grams, change everything to moles, divide each by the smallest. This is a step that students sometimes forget to do. And then when you get to this point, look for whole numbers, halves, thirds, or quarters. In this situation, because we had the half, we multiplied everything by 2. If you ended up with thirds, 0.33 or 0.67, you would triple everything. And if you ended up with quarters, 0.25 or 0.75, you would quadruple everything. And we'll see some more examples like that as we do our work. I want to do another example problem with you, so let's switch to the next problem. And the next problem says, a 10.150 gram sample of a compound known to contain phosphorus and oxygen yields 5.717 grams of oxygen. Find the empirical formula of the compound. So again, if we think of that little flow chart, we did percent to grams to moles to the ratio. This time we're not starting with percent, we're going to start directly with grams. But in this problem, they say a 10.150 gram sample of a compound, that's the mass of the whole compound. So I know that I'm going to have a certain number of grams of phosphorus, and it tells me that I have 5.717 grams of oxygen. So I've got to subtract 10.150 minus 5.717. That will give me the mass of phosphorus. There's a little trick there in the beginning. Make sure you're paying attention. So 4.433 grams of phosphorus. So now we're at the same point we started the last problem. Grams to moles. So we'll do our conversion. And I'm going to look up these molar masses on the periodic table. Phosphorus is 30.974. Oxygen is 15.999. Do some math. Okay, So when I divide, I get 0.1431 moles of phosphorus and 0.3573 moles of oxygen. Again, a lot of students will forget to do that step to get from moles to ratio where you divide each by the smallest. So let's do that. The smallest is 0.1431. Okay, so that's going to be 1. And then 0.3573 divided by 0.1431 comes out to 2.4968. So we're going to make that 2.5. So for this one again, we're going to double it because we have this half right here. So this will be 2. 2.5 times 2 is 5. And if we look back here, the elements that we're dealing with, we can make our formula P2O5. Again, empirical formula, is it the smallest whole number ratio? 2 to 5 ratio, yes. That number, those numbers can't be simplified or reduced at all. That is the lowest whole number ratio. So that's the empirical formula and the answer we were looking for, P2O5.